Okay, so here's what we were talking about last time. We were talking about linear transformations. And more specifically, though, shorthands, a shorthand for representing linear transformations, namely as a matrix. And the big point to realize, aside from the fact that a matrix represents a linear transformation, is how the matrix represents the linear transformation. And that is the columns are the images of the standard basis vectors. Huge point. Right, most important thing, in my opinion, to understand about matrices. The most fundamental thing to understand about matrices. Okay, so we talked about how to use this fact, that matrices are representing transformations and how they are doing so by way of columns, to make an argument about how unavoidably this really has to be the underlying motivation for what it means to multiply a matrix times a vector. And if it's going to be that, then it sort of has to be this. In other words, matrix vector multiplication has to work by way of that formula that y'all all saw in high school, but I think a little better, this formula that shows how matrix vector multiplication relates to linear combinations. And it's hard to see it coming in advance, but both of these formulas relate the matrix vector product to interesting other mathematical objects, dot products, linear combinations. But it turns out this one's underappreciated, as it turns out. I think because of the fact that students don't see it in high school and therefore assume that it must not be that important. It's just absolutely false. It's a very important point of view. So, okay. Okay, then we talked about what it would, same line of reasoning. I mean, if matrix represents a linear transformation, this really has to be our motivation for what the sum of two matrices ought to be. All right? What else could possibly make sense if matrices effectively are linear transformations, and if we have a pre-existing idea of what it means to add two linear transformations, namely functions, right? Then shouldn't that dictate what it means to add two matrices? And you go through and you follow through the arithmetic, and you get exactly the formula that you would expect. You just add one entry at a time, sort of corresponding entries. Okay. So that's where we left off, and the question we face now is, what does it mean, or what should it mean, to multiply two matrices? Well, I mean, again, we're going to try to motivate this based on, well, what are matrices? What do matrices most fundamentally represent? Again, linear transformations are what they represent. And so let me remind you of a fact about functions, is you can compose functions. Now, very important, if you're going to compose functions, you can only do so if the target of the first linear transformation, the first function, is the same as the domain for the second function, right? You can't have a square peg round hole situation when you're composing. If it doesn't fit, you can't compose them. Right? So keep that in mind, right? So that is a requirement that we're going to have to, pay attention to when it comes down to the result we're about to derive. So, but if this does match up, if the target of T is the same as the domain of S, then you can compose those two functions. The notation that we use for composition is that notation right there. Again, I think y'all have all seen this in Calc 1 classes. I mean, you can't talk about the chain rule without talking about compositions. This is how you write it. Okay. Well, let's talk now about what matrix. I mean, if I were to try to use a matrix to represent a composition of two linear transformations, what should that matrix be? How should I think of that matrix, and how ought it to relate to the matrix representing the two linear transformations individually? Okay. So, here's some observations. If T is represented by a matrix A, that means that, the application of T is the same as multiplication by A. Right? We've already sort of, made that convention. Likewise, S maybe is represented by some matrix B. Right? So the composition, which consists of first do T, then do S, is achieved matrix-wise by first multiply on the left by A, then multiply on the left by B, and for crying out loud, that really ought to be this, shouldn't it? I mean, how weird would it be if we were developing an algebra with a multiplication that wasn't associative? It's unthinkable, right? I mean, we feel like we really have to have that property, and I claim that we're kind of done at this point. What this means is that we really have to make the choice that the composition should be represented by the product BA. Now let me say that the other direction. When we get around to defining a product of matrices, it kind of has to be based on the composition of the corresponding linear transformations. Okay. So that's the choice we're going to make, and that's the classical choice. And let's reason through. What does that look like in practice? This matrix A, I'm going to need to make reference to the rows of the matrix A. I'm going to need to make reference to the columns of the matrix A. So we're going to number those. We're going to label those like this: capital letters for rows, lowercase for columns. It's a fairly standard convention. So I'm just going to get on board with that. Likewise, for the matrix B, capitals for rows, lowercase for columns, with a subscript indicating which one. Okay. So, columns are images of standard basis vectors. We just got through agreeing that the product should be based on the composition of the linear transformations. So this is just, the sort of the writing down of our, the convention, the motivation that we just decided on. Columns are images of standard basis vectors. And then you can write down what it means to compose. That's just what it means to compose two functions. T is executed by A, S is executed by B, and we already have rules for how to multiply a matrix times a standard basis vector. This is really just a revisiting of columns are images of standard basis vectors, right? Because you look at this thing, that says the jth column of A is the image by multiplication by A of the jth standard basis vector. So columns are images of standard basis vectors. I told you it was going to come up a lot, right? Okay. So we're largely done with our formula. We just need to interpret a little bit, but this is going to answer most of our questions for how do you in practice multiply matrices. When you multiply matrices, we're going to think of that process as being computed one column at a time as follows. The columns of the product are the left matrix times the corresponding columns of the right matrix. That's the rule. You always multiply by the left matrix, so you look at the corresponding columns of the right matrix to multiply by the left matrix to give you the corresponding columns of the product. And we already know how to do, matrix vector multiplication. Right? We talked about that last time. There's several different points of view, couple different points of view anyway on how to do matrix vector multiplication. Okay, so let's write that down. And by the way, I didn't write down what I just enunciated, but I think it's a good point of view that the columns of a product are B, the left matrix times the columns of the right matrix. I think it's a nice point of view. You might want to jot that down yourselves. What I did write down is an expansion on that based on how do you multiply a matrix times a vector. And here they are. There's a couple of them. The columns of the product are, I'll take it, yeah, sure. The columns of the product are, how do you multiply B times a column of A? Well, linear combinations of the columns of B, where you use the corresponding column of A as your coefficients. Right, so this is a nice rule. The columns of the product come from the columns of the right matrix, in the sense that those columns of the right matrix tell you how to take linear combinations of the columns of the left matrix. Okay, now I feel quite sure that those of you who saw matrix multiplication in high school did not see this point of view. Okay, because that's the linear combination of columns point of view on this product. But now let's take a dot product point of view on this matrix vector product right here. Right, dot product point of view says we would be looking at, well, the rows of B dot this column, that being the corresponding column of A. And so that gives rise to this second interpretation that we're actually going to make a definition. You compute the elements of this product as dot products of the corresponding row of the left matrix and the corresponding column of the right matrix. And you see that right here. So, for example, if you want to compute that entry of a matrix product, that's in the first row. So you look at the first row of the left matrix. That's what we mean by corresponding row. It's in the last column. Therefore, we look at the last column of the right matrix. That's what we mean by corresponding column. Right? And you do the dot product as indicated there. Okay, this is the formula that I suspect y'all saw in high school, right? And again, now computation, it comes down to actually, cranking arithmetic. Yeah, I think this is hands down the easiest one for the purpose of doing the nearly trivial task of just cranking out arithmetic, right? So it's the best method for the least interesting problem. That's one way to say it. So again, don't fall too much in love with this as a way of thinking about matrix products. This ends up being really, really important in a lot of applications. And then it turns out you can make an argument where you come to this conclusion as well. In the same way that you can think of the columns of the product, you can also interpret the rows of the product. And it's harder to see this without doing a little bit of algebra, but the rows of the product are also linear combinations. Now, importantly, they're linear combinations the other way. The rows, they're not linear combinations of the rows of the left matrix. They're linear combinations of the rows of the right matrix. It was the columns of the left matrix. It's the rows of the right matrix. And use the corresponding row of the left matrix for your coefficients. So if you look at interpretation 1 and interpretation 3, there's a lot of similarities here, but there's some important differences. It's rows instead of columns, and it's right instead of left, and it's left instead of right. Okay, so importantly, big perspective, all three of those come out of looking at this formula right here. This formula was motivated by this choice where we decided that, look, a matrix product really kind of has to be based on compositions of linear transformations. So that's, the motivation, the origins of these formulas are really important to understand. Okay, so let's do some arithmetic. Let's crank this one. Suppose you want to multiply these two matrices. I'm going to start by doing this from a columns point of view. Let's compute the first column of this product. The first column is going to be a linear combination where we use the first column of the right matrix as our coefficients. And you can see those numbers right here. 5 and 6. First column. Right? Now, linear combinations of what? Well, we use the columns of the left matrix as our, that's what we're taking linear combinations of, right? In order to get the first column of the product. It's always linear combinations of the left matrix columns, right? So, ditto here as well. If you want to compute the second column of the product, it comes from looking at the second column of the right matrix as your coefficients. All right, everybody see how that works? Okay. All right. Okay, now let's do the same arithmetic. We're going to multiply the same two matrices, still this times that. Here I'm going to do it from the high school point of view, and that is dot products, just corresponding dot products. So, for example, if you want to compute top left element, well, that's in the first row, so you take the first row of the left matrix. It's in the first column, so you take the first column of the right matrix, and you do that dot product and you get that value. Now, again, this is the one you saw in high school, probably. Okay. It gets down to the same final answer. In fact, you can even see the same arithmetic happening. You know, where did this 23 come from in this argument? Well, it came from the computation of the first column, specifically the first entry in the first column, and that first entry was computed as a dot product of those numbers and those numbers, namely the first row of the left matrix, the first column of the right matrix. So it's easy to see that these will always give you the same answers. Yeah.
If we are finding if we are inventing the matrices when we see a situation involving vectors and linear combinations, is the left matrix just going to be the second transformation?
It is the second. Yeah. So and there's this awkwardness of notation of how you write things down. The one that's second. And there's this urge to think of that as being the one on the right, because when you make the diagram, and generally we live in a left to right culture, and so the one on the right you think acts second, but tragically the way functions are written down, it's the one on the left, and that's just because of this. I mean, we read it on the left there because by acting second, it's on the outside, and outside the way functions are written is on the left, and it's just right. It's super maddening. But yeah, right. So what you said is accurate. By the way, this cultural aside, there is a very small group of mathematicians that are so frustrated by this fact that they write functions in a different way. And instead of writing, what we write is, if you have some value x and you plug into the function, we write f of x, and you can see right there how, it looks sort of backwards. The x was on the left over there, but it's on the right over here. These other mathematicians write it like this. And the problem goes away. And from a certain point of view, they're right to do this. But it's a pretty weird point of view, and nobody else wants to do it that way, and cultural forces are very strong, and the institutional momentum of doing it not that way, but the institutional momentum of writing functions this way is so deep that I don't think it's going to change. It's certainly not changed at this point, right? And I think it's funny that they're trying to do a good thing to math notation, but it's not helping. Okay. Now let's take a linear combination of rows point of view. Now again, same arithmetic, same two matrices on a multiplying, but instead of viewing this product as being a linear combination of the columns of that matrix, we're going to view the product as being linear combinations of the rows of the right matrix. And so you see that algebra here. Here's the rows. We're taking linear combinations of the rows of that right matrix. Linear combinations how? Well, we're going to compute the first row. Green, sorry. We're going to compute the first row here as a linear combination in which we use the first row of the left matrix as our coefficients. Right, first row of the left matrix in yellow, 1 and 3, those are our coefficients. And you can see that gives us all the same numbers. Right? We use the second row as coefficients to compute the second row of the product. see how this process works? Okay, so bunch of exercises for y'all along these lines. Good stuff. And we're going to declare victory on Chapter 3 now. Moving on to Chapter 4. Finally getting into derivatives. We're, here it is, into the 4th chapter of the book, and we're finally getting around to talking about derivatives. It seems a little silly. But there's just a lot of preliminary work that has to be done, right? So now we understand multivariable functions and multivariable context and multivariable communication in the form of equations and what these look like and how to understand them. And we have proper tools for understanding derivatives in the form of linear transformations. And with all of that work done, we can actually get started on calculus. Okay. All right. So I've already pointed out that we have this interpretational problem with calculus, in that if you try to just rip off the good old plain old definition of the derivative from Math 111L, right? You find yourself writing down this. And then realizing that we can't divide by a vector. That doesn't make any sense. So crash and burn. We cannot use the old familiar definition of derivative. So we're going to have to kind of come at it from a different point of view. So here's the different point of view on single variable derivatives that I want to take. Let's forget about what I'm going to call the fraction point of view on the derivative. Right? Just pretty much let that go. I mean, we're going to come back to it here or there momentarily, but it's really not going to be the point of view we're going to take in this course. So here's a different point of view. And this is what I'm going to call the factor point of view. So y'all remember this formula for linear approximations of functions? This is Calc 1, ancient history, right? And you can take this term and move it over to the other side and rewrite it as delta f is approximated by the derivative, df dx, times delta x. So this is one of the big points of view I want to take, that the derivative, don't think of it as a fraction, think of it as a factor. Yeah? Everybody good? And so I hope this isn't news to anybody. By the way, here's a highly analogous to this is this point of view on the derivative. Now y'all would recognize this as the chain rule, right? Leibniz form of the chain rule. And there's this urge to cancel the dx's or something, and maybe in a certain point of view, but that rubs my fur backwards. I'll explain more about that when we get to talking about the chain rule in this multivariable context. But so anyway, this is the chain rule that y'all have seen before. And notice that again, if you have f as a function of x, you can think of it as a factor that you multiply by the velocity of the input x to get the velocity of the output f. Right? So again, this point of view isn't really pushed in single variable context, but that is an interpretation that can be made of the chain rule, that derivatives can be thought of as factors. Yeah? Everybody all right? Okay. So this point of view of thinking of the derivative as a factor, specifically the factor that you multiply by, notice, input changes, be they discrete changes, instantaneous rate of change. It's what you multiply by input changes to get output changes. Again, either some discrete change that we approximate or a rate of change, namely like a velocity. Right? So this is the point of view that I want us to take on derivatives. They're factors that you multiply by input changes to get output changes appropriate to the context of your situation. Okay. All right, so here's a picture that you can draw to represent this. Here are the input. Oh, I've already forgotten what colors I used. Input changes in yellow and blue. The input changes. You could think of it as, look, I'm at this point and I'm contemplating what would happen if I moved by some discrete amount, and I want to be able to compare when I change from that input point to that input point, what is the corresponding change in the function, namely that value compared to that value. Oh, which I should have had a blue. Oh. So an input change compared to an output change. Now, again, the urge is to think of, oh, well, if it's a factor, then it's a fraction. If it's a fraction, then it's a slope. And in the single variable context, that makes sense. Yeah, I know. Right. So set that aside. Right? So I want to focus right now just on viewing this as a factor. Okay. So analogously, suppose this point is moving as a function of time, right? And maybe it has a velocity, dx dt. And we could very reasonably ask them, well, if that is moving with some velocity in the input, then the output's going to be moving with some velocity as well. And the derivative df dx can be thought of as the factor that you multiply by the yellow input vector to get the blue output vector. Okay, just pictures representing what we already talked about. Okay, some examples. These are straight out of Calc 1. I'm going to let y'all read these examples. The last thing I want to do in this this first section is just redraw these pictures. So we have these input vectors. Those input vectors are in the domain, and I've drawn the domain as the x-axis on the graph picture here. And let me remind you, graph pictures are weird. This is a two-dimensional picture representing a single variable function. That's weird, right? It's kind of unnatural. And likewise, there's a one-dimensional target here. These changes represent changes in a one-dimensional target space, R1, and yet they show up as axes in a two-dimensional system. So it's kind of unnatural. What I want to do is just pull these apart, right? The same setup. I have some value x, and I'm either making a discrete change or making an instantaneous rate of change. I just don't want to draw it in the graph context. Let's draw the domain separately. Here's an x-axis in which I can talk about a discrete change or an instantaneous rate of change. And then here's our target space in which there is either a corresponding output change or a corresponding output velocity. And our function, domain to target. And this is a more natural, really, way to represent a function. As the domain's on the left, the target's on the right. The domain and target are separate spaces. Why? Let's draw them as separate spaces. Let's not rely on this fairly artificial, admittedly convenient, but fairly artificial point of view of graphs. Okay, so we're going to have to take a quick aside before I continue on with this point of view. But when we come back to it, this is the point of view I want to take, namely, we have a function with a domain and a target, and I want to think of the derivative as a relationship between input velocities and output velocities. Or let me say that more generally. Input changes and output changes. Appropriate to the interpretation. Okay, so now we do have to do a quick aside. The way I want to present derivatives in this class, I need to do derivatives of parametric curves first, and it doesn't really quite fit into the mold of what I was just talking about. In fact, a parametric curve, for example, this position as a function of time, a single variable, and of course we often view it as time, t. It's arguably not even a multivariable function. If you think about it, I would pose that you could think of a parametric curve as kind of a combination of a bunch of single variable functions. I mean, specifically, let's look at that component there, the first component. That is literally a single variable function. T is the one input variable. R1 is the one output variable. That is a Calc 1 function, right? And the parametric curve is just made up of, just an ordered list of those single variable functions. So it's not really even quite multivariable as a function. It's just a bunch of single variable functions. Okay. If there were multiple input variables, we could not make that case. The input variables would be unavoidably connected together. Okay. So being as it is basically a single variable function, I'm going to make an attempt here to define the derivative using the single variable sort of analogy. I mean, here's what we would write down if we wanted to just shamelessly rip off and steal from our existing definition of derivative for single variable functions. Hope it looks familiar, right? It's exactly the same thing. And it turns out it's totally fine and, in fact, quite useful and very natural, as it turns out. So this is our definition. Now, bad news. Remember, way back when, long time ago, the very first time you saw the definition of a derivative, what happened next is you had to go through and compute directly from the definition a bunch of, like what happens if the function is a monomial. Go through, expand by the binomial expansion, and stuff cancels. You make arguments about limits, and out comes an answer. And then you try different things, and eventually you start coming up with rules. And we had to kind of from first principles build up these rules that we used to, day in and day out compute derivatives. And that whole business about, x to the n, and you take the n and bring it down, that's a rule that we derived from this definition. From a definition that looked just like this. So the bad news is, here we have a highly familiar and yet technically new definition. It is different, right? Because it's for multivariable outputs. Do we have to start all over with our rules? Do we have to start plugging in different things, notice patterns, use the binomial expansion? There's a point of view that says, the assumption, the default assumption should be yes. There's totally different context. You've never seen, Calc 1 does not traditionally talk about functions of this sort, and so we can't just, rampantly speculate that all of our old rules should work. That's the bad news. Here's the good news. Turns out they do work. But I like to lead into that dramatically, though, because this is something to appreciate, right? You can't assume it would be true. When you can't assume something, the default assumption should be, it's probably not going to work out. So it's wonderful that it actually does. And here's the argument. This definition of a derivative of a parametric curve, you can just break it down one step at a time and notice that every single step in that formula is done component-wise. So specifically, when you subtract two vectors, how do you subtract vectors? You do that one component at a time. Right, this is what it means to subtract one component at a time. Okay, now we have a vector divided by a scalar. How do you divide a vector by a scalar? Well, good news. You do that one component at a time. Now, we haven't talked about limits yet, but I'm going to make an assertion that y'all will see backed up when you watch that video this weekend. But when you take limits one component at a time. And so, in fact, when you're taking a derivative of a parametric curve, the components of that derivative are good old, plain old Math 111L, Calc 1, single variable derivatives. They are exactly, one component at a time, they are exactly the derivatives with which we already have powerful tools like the product rule and the power rule and the chain rule and the quotient rule. All that stuff comes along for free. One component at a time. So that's tremendously convenient. So so this choice here, we made this definition, with a kind of a question mark attached of, is this a good idea? It seems like a reasonable choice, but does this work out well? We have one highly supportive yes to that because it's going to be computationally very convenient. That's super. Okay, now, computationally convenient. The refinement of multiplication tables that I came up with when I was in first grade or whatever that was, also computationally convenient. So that alone, not persuasive, right? So why, we naturally next ask, why is this a natural? What is it that's geometrically or physically natural about this definition? And it turns out that there's a great answer to that as well. Here's our parametric curve floating along through space. Here's where I am at time t. Here's where I am at time t plus h. There's that difference vector. Now, as h gets smaller and smaller and smaller, those 2 points get closer and closer and closer and closer together. But then I'm also dividing by a smaller and smaller denominator, h. And I appeal to your intuition, and I don't want to be rigorous about this. This is not what Math 212 is. But in the limit, let me say that differently. For small values of h, you would expect the fraction to not be something that's approaching 0, but to be some vector that stays, in the realm of the finite of length. And then in the limit as h approaches 0, and again I appeal to your geometric intuition, as these 2 points get closer to each other, the secant vector connecting those 2 lines becomes a tangent vector to the parametric curve. Pretty plausible, highly analogous. Right? Okay. So this thing that we've called the derivative, this definition that we're hoping to have something geometrically natural about it, it's a tangent vector to the parametric curve. That's really nice. It turns out it's even better than that. It's not just a tangent vector. We can talk about its length. The length of this derivative that we've defined. Here's our derivative. Take the magnitude. There's the magnitude. And let's interpret what we've got here. Notice we're taking a limit as h approaches 0, but we have the magnitude of that difference vector. That's distance. Right? We have distance divided by time. And in the limit, distance divided by time is speed. So the magnitude is speed. All right, so this is shaping up very natural. This derivative vector that we've written down, it's a vector that points in the direction our particle is moving. Its magnitude is the speed of that particle. Where have we heard this formulation before? A vector whose direction is the direction of motion and whose magnitude is the speed. Day one of class, when we were defining vectors in the first place, we called this the velocity vector. Right? Direction of motion, magnitude being the speed, that's velocity. Okay, so that's a really fantastic punchline. This thing is very natural. I do want to point out a little subtlety here. We got this idea in the first place from a definition that we wrote down anticipating or trying to understand slopes, right? Remember back to Calc 1? Nobody said anything about speed on when you were motivating derivatives. The big point of discussion is let's find the slope of the tangent line. So this was motivated to be slope of the tangent line. In this multivariable context, the way I've set things up, it's not the slope of the tangent line. It's the velocity. It's not the same thing. You know? Why? Why did I get such a different answer? Well, it's because of context. In Calc 1, this is we motivate this as being slope of the tangent line, but let me say that a little bit more carefully. It's the slope of the tangent line to the graph. In Calc 1, you're looking at graphs, right? So in the graph context, calculus means one thing. In the graph context, in Calc 1, derivative means slope. We're not looking at a graph here. This is not a graph. This is the image. It's not a graph, right? So, like I was saying all throughout Chapter 2, right? If you're looking at a function, if you're representing a function with a different kind of a picture, graph, image, level set, right? The context of how you're representing the function geometrically, you're going to get totally different interpretations of the calculus. So this is a great example, right? I mean, students that don't appreciate the difference between, a picture representing a graph and a picture representing an image would expect and assume that, well, shouldn't the derivative be the slope somehow? I don't know, maybe the slope of that tangent line. And it's completely not. It's not slope. It's a vector, right? It's completely different. So anyway, this is what I was talking about there, that, making an appropriate interpretation of calculus requires that you are highly aware of what kind of way are you representing the function? Which context are you in? Okay. All right. Okay. I will say, by the way, that once you've defined the derivative in a Calc 1 class, then you do probably end up doing some scenarios where you have a car driving along a road, right? And that car driving along the road, you write down formulas for how fast is it moving, and you eventually notice that, oh wow, look at this, in this scenario of a car driving along a road, one-dimensional road, of course, that the derivative is the velocity of the car. And they don't say parametric curve in that context, but what is happening in that, the application to cars of derivatives is the car is a parametric curve in R1. Now, you can't say that in a Calc 1 class, right? But that's what it is, and that's why that analogy works out very well here. Okay, enough of that. Okay, so suppose we have birds flying along. And we know the position of the bird is a function of time. Now, by the way, let's recognize this as this is a parametric curve we've studied previously. This is the helix, right? Because the xy coordinates are going around in a circle. The z coordinates going up at a constant rate. So this is a bird that's like caught an updraft and is doing a spiral upward kind of a deal. So, reasonable question. What's the velocity of the bird? Okay, well, velocity is derivative, as we just argued. Right, velocity is derivative. As we argued earlier, the derivative of a parametric curve has components that are the derivatives of the individual components of the parametric curve, or said differently, derivatives of parametric curves are computed component-wise, one component at a time, right? So those are two big arguments that we made, and notice what we've reduced the problem down to. We've reduced the problem down to 3 Calc 1 questions. Looking at that first component, time derivative of cosine t. That's very, very literally Calc 1, right? There's no multivariable calculus happening in that calculation, and so you get to use all your old familiar rules, trig derivatives, product rule, chain rule. It all comes along for free. Likewise, the derivative of sine is cosine. The derivative of t is 1. By the way, I'm going to comment here and probably several more times throughout the course. All those old rules for derivatives, got to make sure you're really good at them because it's going to come up a lot in this class. I'm going to assume that you're just really good at the chain rule and really good at all the trig rules and power rule and this kind of stuff. So product rule. Okay. So if you're a little rusty on your Calc 1, definitely want to brush up. It'll be very important. Okay, here's a kind of question that I think might look familiar. There's a category of Calc 1 questions, about cars on roads and stuff that fit into this category where they tell you, look, something's moving, and here's its initial position, and here's velocity as a function of time. How do we figure out what the particle's position as a function of time is? Right? So it's a matter of taking an antiderivative, and again, I hope you all have seen Calc 1 versions of this before. So here's how it works in this context. It's really very much the same thing. In the same way that velocity is a derivative of position, position is an antiderivative of velocity. Derivatives are computed component-wise, and so I hope it's no surprise, antiderivatives are computed component-wise. This antiderivative of a vector-valued function is just a vector of individual antiderivatives. These individual antiderivatives, these are all Calc 1, right? So again, make sure that you're good with your Calc 1 and that you're comfortable with all of those. Those are relatively easy ones, right? Anyway, make sure that you're strong with your antiderivatives. And let me remind you, there's a lot to antiderivatives. There's stuff like the power rule. There's memorizing that all of the trig derivative rules go the other way, right? But then there's also stuff like substitutions, integration by parts, trig substitutions, I think, are really important. I make the case of how important trig substitutions are based on the fact that the world is full of circles. That's where trig comes from, circles. The world's full of them. So trig substitutions are really, really big deal. Those of you who are engineers are going to make massive use of trig substitutions, for example. So we're most of the way done with the question at this point. I do want to recognize a standard landmine that students tend to step on at this point. A lot of students say, okay, and we have these constants that we have to evaluate, and very large number of students say, and the constants are the initial position, and so 3, 2, 5. It's just not right. It's way wrong. It's really wrong. Now, let me explain where this typically tends to come, why students make this classic blunder. And it's because they've been given unrepresentatively easy questions, where instead of having trig involved or something like that, these are always like polynomials. And so, for example, they might be stuff like, t and t squared and t cubed. Right? Well, that makes these things down here also polynomials. But specifically, that makes these polynomials that have a factor of t, guaranteed. And then when you plug in t equals 0, all those things disappear. And as it turns out, in the case of nothing but polynomials, the initial conditions are the integration constants in a fairly broad collection of cases, but for algebraically coincidental reasons, right? So anyway, it's logically garbage to say that the initial conditions are the integration constants. It's total garbage from a mathematical point of view, and the fact that it ends up being that way by coincidence is highly deceptive. And so lots of students make that mistake. Of course, what we have to do is plug in, at t equals 0. When t is equal to 0, I know that position is 3, 2, 5. That allows me to solve for these constants, which are not 3, 2, 5. Yeah, so we get these numbers here for those constants. Everybody happy with that? By the way, this is a good opportunity for me to point out another thing. So let's suppose that on an exam, hypothetically, and this will happen, suppose that a student writes, none of this and just plugs in those numbers and gets a 3 here. And let's talk about how that would be graded. And this is just an FYI, just in terms of, how to do well in Math 212. Let me remind you, this is not a course about answers, it's a course about ideas. Right? And so when I'm grading an exam question, I'm thinking about based on what's written on the page, what can I infer that the student understands? What ideas relevant to this question does the student understand? And what is their level of proficiency in executing that? It's a combination of things. So if a student has done this, they have seemingly indicated that they have no understanding of how to evaluate the integration constants correctly. So I wouldn't give any points concerning the integration constant. And of course, maybe they got the antiderivatives right. Cool, that's points. But concerning the integration constants themselves, I wouldn't give any credit for that. Students might look at this and say, I got 2 of the 3 coordinates correct, right? So I want to point out, again, it's not about the answer. Yeah, I can see that 2 of the 3 are correct, but the idea that's been communicated by this hypothetical student is absolutely invalid, with no mathematical basis. And that's what the grading is going to be based on. So anyway, heads up. I don't want to surprise you all on the exam with, oh man, he took off a lot of points for, I got 2 of the 3 things correct. It's the wrong way to look at it. Does that make sense to everybody? Okay. All right. That was just an aside. Okay. Okay, so a bunch of exercises. By the way, notice that this section, the exercises, the numerical order that they're written down in is not the same as the chronological order in which I wrote these exercises. Some of these exercises came, like a year or two after I first wrote through. So this is a great example of why I use these permanent exercise labels. I use these permanent exercise labels so that, for example, having made a video recording already, maybe, I don't know if I have, but let's say if I've already made a video recording for this one as number 6, right? That when I go back at a later date and insert extra exercises and all of a sudden it becomes number 10, I don't want there to be this mass confusion between, the old recordings and the new labels in the book. So this is why I remind you, I urge you, don't pay any attention to these numbers, right? The syllabus will not make reference to these numbers. The video recordings will not make reference to those numbers. It's these permanent exercise labels that you should always look at. And so, heads up. Yes?
So does it make life easier on the TAs who are grading the homework if we do it in the order of permanent labels or in the order of...
that's a great question. Oh, man. I'm thinking... No. Here's the right answer to that question. The reason I stuck these questions in where I did is because I want you to do them in the order that they're written down. Let me do it like this. I want you to do them in the order that they're written down. I put this exercise in here because it's going to be useful in these exercises, right? So I want you to do them in this order, but label them with these labels. That's a great question. Thank you for asking that. Does everybody understand the motivation there? So do them in the order that they are presented, but label them with the permanent labels. Okay. Yeah, great. Okay. Now, so I want to talk about some of these exercises. You'll see there's quite a few of them let's see, where does it start? So there's quite a few of them that are lumped together here. And these are going to, they're lumped together because they're all kind of part of the same purpose. All these exercises are intended to help y'all sort of go through the discovering experience of developing the idea of curvature. So, how do you define curvature of a parametric curve in R2 in this case? And then likewise down here, several exercises on how do you do curvature of parametric curves in R3, and it's a little bit different in R3 than R2. So there's this is a themed group, a couple of themed groups of exercises. That said, I want to walk y'all through some of the interpretation of what is going on here. By the way, I put these exercises in here to guide you through those calculations, right? So if I were to just say, compute curvature. Right, that's way too hard of a question, right? So I break it down into like 5 steps in the form of 5 separate exercises to guide you on a path that would get you to where I want you to get. All right. They're like little mini labs, kind of, sort of. Okay. All right. So anyway, I want to talk you through the context a little bit. So let's look at R2 for starters. So let's focus our attention here. Forget about all of that for the moment. And suppose we have a parametric curve. Like that. There's a curve that maybe I have parameterized. What should it mean to talk about the curvature of that curve? How curvy is that curve? Right? So there's different ways that you can go about defining this. One choice that you could make, and a reasonable point of view, is to say, find the circle. Let's see if I can do better than that. Find the circle that's kind of the best, approximating circle, and then compute the radius of that circle, and we'll define curvature to be the reciprocal of radius. Right? The bigger the radius, the smaller the curvature. Right? As illuminated by the fact that the Earth, with an enormous radius, has so little curvature that people didn't even notice, right, for a long time. Okay, so that's one way to go. A more direct way to go, an easier, ultimately, way to go, is to do as follows. We'll look at the velocity vector of the parametric curve. Velocity vectors are tangent vectors. There's a related object called the unit. tangent vector. This is a vector of length 1 pointing in the same direction. You all know how to compute those. We'll then look at the angle that we're going to call phi, no relation to spherical coordinates. Apologies, I'm just getting on board with a convention. Look at this angle phi, right, and ask how fast does that angle change as you move along the curve. So specifically, if you've moved a certain distance along the curve, as you continue to move, how fast does that angle change, right? So what is the rate of change of phi with respect to s? That's the definition that we're going to go with of curvature. Correction, absolute values. Curvature is an intrinsically non-negative thing, kind of like distance. So that's the definition. Now, how do you compute d phi ds? That's a whole nother matter. It's a tricky process. That's why I have, again, several exercises that break this up into little steps. And how do you get your hands on d phi ds? And if you follow the hints, trust me on this. Follow the hints. Stay on the path. Right? It'll all work out. And you get some nice formulas and related exercises concerning what is how do you actually do this. Now let's think about how to do this in 3 dimensions. How would I define curvature for a 3-dimensional parametric curve? And the tough challenge is, which angle do we talk about? I mean, I can talk about distance along that curve, right? If I'm going that way, for example, I can talk about having started from there, how far. What is s? Something you can talk about. But which angle are we talking about? There's kind of 2 different angles that define a direction. There's the, this kind of angle, right? And then there's the vertical. There's the horizontal and then there's the vertical. So do you look at the rate of change of one of them or the other one? Or both, and then you add them up? I mean, it's hard to figure how you can use that point of view. So, in fact, it does not translate well. So what we do is we come back here and we explore this vector. Not the rate of change of angle, but the rate of change of this tangent vector, t. And now, t is a vector, so dt ds is a vector. But it turns out that dt ds has a magnitude which is always equal to the exact same curvature that we already defined. So the magnitude of dt ds is a definition of curvature, and that makes perfect sense in this 3-dimensional context. dt ds, and we can still talk about this tangent vector t. We can still talk about how fast that tangent vector changes as we move along the curve. And this makes for a good starting point for the conversation. Now, how do you compute that? And that's kind of hard, as it turns out. So again, there's several steps in the process. Stay on the path. Follow the hints. Right? So some objects come up in that exploration. I just want to point out what those objects are. When you're moving along a curve, at some given instant, you can talk about the plane of motion. The plane of motion is a plane that's defined by, at the given point you're at, what's the direction that you're going, and what's your acceleration. Your acceleration is another vector, which, among other things, is going to tell you what's the direction perpendicular to the direction of motion. So the other direction of this plane. So if you want to talk about vectors in this plane, such as acceleration, for example, you can relate acceleration to these 2 vectors by way of what are these components. And there's a callback to Chapter 1, components of a vector. Those are dot products. Right? Coefficients in a linear combination in this case. So acceleration is not actually the thing we were interested in. Keep in mind, what we're actually interested in here is dt ds, but it turns out that you're going to be able to relate acceleration to dt ds, and the good news there is acceleration is easy to compute. Right? So again, a very common thing in math is don't necessarily try to compute something directly. If you can just relate something you're trying to compute to something else that you can compute, any relationship between them might help you compute the one you're actually interested in. So that's what happens here, and we end up being able to compute curvature based on studying how all of these various objects all relate to each other. Okay, so again, the series of exercises in the order they show up in the book will walk you through what that process is, and I'm pretty sure that there are video recordings on at least some, and I can't say all, but there should be a lot of video recordings to help you with this process. Stay on the path, follow the hints. Okay. All right. Okay. All right. So now let me go back a little ways. Here was our point of view on single variable derivatives, right? Remember, we want to reinterpret derivatives. Forget about slopes momentarily. We'll come back to it later. We're reinterpreting derivatives as a relationship between input changes and output changes. Specifically, hopefully we'll work up eventually to realizing it as a factor that relates input changes and output changes. But for the moment, just a relationship between input changes and output changes. So we're understanding the function, right, as a function from a domain to a target, and the input changes live in the domain, the output changes live in the target. The changes are represented by vectors. Sure, because there's a direction that I'm maybe moving, right, either as a discrete jump or as a velocity, and there's an amount. How far did I jump? How fast am I moving? So direction and a magnitude. So vectors that we use to represent the input changes, and likewise vectors that I use to represent the output changes. Okay. So a derivative, I'm just saying the same thing over and over again, slight variations each time. A derivative is a relationship between an input vector and an output vector, with the understanding that vectors represent changes of whichever sort, depending on the context. Okay, input vectors and output vectors. All right. So let's go with that in a multivariable context, looking at this picture. Here's my function. I've got a domain. I've got a target. Now, as I've drawn it here, there's a function from R2 to R2. And, maybe I'm sitting here at this point, at which point my image is there, that point. And let's speculate on what happens if there's an input vector. Let's see here, color choice, yellow, I guess. What happens if there's an input vector? Okay, keep in mind, input vectors represent changes. I like my own personal preference is to think in terms of velocities. I think it's just easier to think in terms of velocities. So if I have a velocity, and I appeal to your intuition, that red point on the left goes to this red point on the right. If that red point takes off and starts moving with some velocity, well, then the target over here on the right is going to take off and start moving with some velocity. Right? The output value, the output value is going to move with a velocity that is the derivative. The derivative of that, how fast is it moving? Is a bird flying or something like that? So this is what we're interested in trying to figure out how to, get our hands on. Now there's a bunch of stuff to get our hands on here, but the idea is if I'm at some place moving with some velocity in the domain, I want to understand what is the corresponding velocity in the target. Just like the new point of view that we're taking in single variable calculus. Is everybody on board? Does everybody see how this is the analogous thing from Calc 1? Okay. All right. So here's how we're going to accomplish that. And let me remind you that there's all sorts of issues of rigor that are not Math 212 appropriate. I'm sweeping a lot of stuff under the rug, and it's fine in this context. So don't worry about what I'm skipping. Is that a...
Yes.
Yeah.
They're moving the inputs and outputs. They're moving with different velocities.
Yeah, presumably. Yeah, I mean there might be some coincidence in which, yeah, but we certainly cannot assume that they move with the same velocity. Yeah, that's right. Anybody else? Feel free. Okay, so let me do a little bit of foreshadowing. You're going to see lots of different kinds of derivatives in this class. 5 or 6 of them. As it turns out, all slightly different kinds of derivatives. Strong argument can be made that this is the one that should be your fundamental sort of cornerstone, deep down point of view on what a derivative is there's an input velocity. What is the corresponding output velocity? Okay. All right. And all of the kinds of derivatives that we're going to come up with are all going to be related to this in some way or another. Either different ways of answering this question that we've brought up here, or different aspects of the answer, different applications of the answer to this question applied in certain contexts. They're all related to this. Okay. So how am I gonna figure out what that output vector is? This is very brute force. This is very blunt. What I'm about to do is, I don't know, kind of analogous to, you remember in Calc 2 or I guess late Calc 1, and you were trying to compute the area under the curve, and well, I guess we could take this area and let's slice it up, right? And let's just write down a bunch of little rectangles. This very brute force, blunt approach. I'm going to do something pretty brute force and blunt here, and I'm gonna for dramatic effect, not reveal if there is a better method that we'll do later. Anyway, so here we go. Here's brute force blunt approach. So you say you're at this point moving with that velocity. I can define a corresponding parametric curve. It's easy to do, right? This parametric curve here. A plus TV. Right? Chapter 1, old news. Okay. By the way, you can take a chapter 4 point of view on this. Taking this as a parametric curve, viewing this as x, a plus tv. You can take the derivative, and in fact, you get v. So this is very literally, this is a curve that when t equals 0 has you at the point A and moving with velocity v. Okay. Alrighty. So that parametric curve, I can plug that in to the function. Right? If these are my input points, then I can just plug into the function f, and out comes my output points, which are going to be, they're not going to be moving in a straight line. I mean, this is not a linear transformation necessary, probably not a linear transformation, right? So the output is going to be some kind of, I don't know, maybe moving around like that, or who knows what it's doing, right? Some curve. But being as it's a parametric curve, that is a function of time. F is a function of x. X is a function of t. So ultimately, this blue curve is position as a function of time. I can talk about its derivative, namely its velocity. So it's pretty blunt, right? It's pretty brute force. I'm just creating the scenario I'm considering, namely being at the point A and moving with velocity v. I'm creating that algebraically, and then just directly, one step at a time, computing what the output derivative is. Everybody on board? Okay. So here's a formula. Parametric curve in the domain at the point A, moving with velocity v, when t is equal to 0, that is. Here, let me zoom in on this. At the point A, moving with velocity v. Plug into f to get the image curve in the target. and then derivative is velocity. Okay, so that's our calculation, and this is what we're going to call a directional derivative. Let me select this. Directional derivative. Oh, come on. Directional derivative. This is a directional derivative. Now, there's little details you have to attach to it. What am I taking a directional derivative of? Of the function f. You have to indicate what you're taking a derivative of. Now, specifically, we're taking a directional derivative at a certain point. Right? I mean, where you are matters. Right? If you're here moving with a certain velocity, that's different from being there moving with a certain velocity. Okay, so you got to indicate where you're at. All of that's familiar from Calc 1. But there's an additional input here, and that is I have to tell you what is my input velocity. Right? This idea of I want to know what the output velocity is depends on what is the input velocity. I can't make this parametric line without knowing what the input velocity v is, so that's part of it's part of the construction. And that said, then this notation here means directional derivative. And again, there's the formula. Here's a picture with all of that represented on it. I pretty much drew this picture on the other page. If we want to say we're at this point moving with velocity v, there's a parametric curve that does that. That's that parametric curve, which you plug into the function and it has this image, some parametric curve, whose derivative then gives me that output velocity there. Okay. Cool. All right, so that's construction. We've got a couple of minutes here. I guess here's the last thing I'm going to do is I'm going to talk about this term directional derivative. There's an unfortunate awkwardness in the use of that term, and it means different things to different people. And I've been surprised to find out how many people who use this term are unaware of the fact that other people using this term don't mean the same thing. It's kind of weird. So anyway, here's the point of view I've given you. You'll notice is that we're taking a directional derivative. We've got a certain vector f, a certain function f at a certain point with a certain velocity, and that velocity could be any velocity, right? I mean, in the real world, your input could be changing at any velocity. Seems like we'd want to define directional derivative to be able to apply universally, everywhere in the real world, and that this velocity vector should be allowed to be any vector. Okay. There is a point of view, not entirely without merit, that says if this velocity here, let's keep in mind that look at the term directional derivative. The argument gets made, well, the word says directional. It doesn't say vector derivative. It says directional derivative. A vector has a direction and a magnitude. If it says directional, maybe we should focus only on the direction and not on the magnitude. So the end result of this is to insist, some people do this, to insist that velocity vector must be a unit vector. And that, as seemingly clear from the use of the word direction in the term directional derivative. Right. So in some context, heads up, in some contexts, this is used specifically to refer to unit speeds. Unit velocity vectors v. And then someone who, makes that use of directional derivative would then account for, in the real world, if they're moving with an actual velocity, and say, well, we're moving, in that direction, we're moving with some speed, and they'll subsequently account for the extra speed with an extra factor. Okay, so I don't like that argument. It seems to me that that's an argument that rests largely on semantics. I don't really, come on, right? I don't know. I'd rather do it this way. So you'll notice in my book I have the term directional derivative defined like this. But I want y'all to be aware that this is that this term means different things in different contexts. And I'm going to have to come back to that again tomorrow anyway, so this makes a great stopping point. And see y'all later. I do have homeworks to return, so please stick around for just a moment.